Why do stars near a black hole get stretched and torn into long, thin strings? Textbooks often explain this phenomenon with tidal forces. The gravity on the side of the star closest to the black hole is stronger, while the gravity on the far side is weaker, causing the star to elongate and flatten, eventually tearing apart. This explanation does mention that gravity has a gradient, but it doesn't explain what is really breaking down at the core of this process. In energy filament theory, gravity is seen as the slope of the tension C at a large scale, and tidal forces are actually the slope of the slope, the appearance of how different parts of the same mass experience varying tension. But the real reason the stars tear apart is not the shape, it's the breakdown of rhythm. A star remains stable because the phase alignment of the swirling motion between countless particles holds everything together. Each particle is like a beat in a vast symphony, where each part of the star must stay in sync to maintain a stable configuration. It's like a large orchestra, where each section plays a different melody, but the overall rhythm must stay unified. Now, if you bring this orchestra close to a black hole, the tension slope becomes steeper, but more importantly, the local time at different radii begins to diverge. The closer a particle is to the black hole, the slower its time becomes, and the farther out it is, the relatively faster its time flows. This is the time gradient. Further down, it turns into a rhythm gradient. The cosmic beat felt by the outer layers of the star differs from what the core feels. The outer particles are forced to slow down, while the inner layers continue at the original rhythm. The phase locking between the layers begins to weaken. Once the rhythm can no longer be synchronized, the large tension slope takes over the shape. Each small piece of matter begins to slide along the slope that offers the least effort according to its current rhythm. The side of the star closest to the black hole now finds itself almost on a vertical downhill slope, while the far side remains on a gentler slope. The middle part of the star, caught between two different rhythms and two different slopes, is caught in an unstable situation. This is when the star starts to transform from a spherical, rhythmically locked entities into a long, stretched-out plasma filament. The front part is dragged away first, the back end cannot keep up, and the middle gets thinner and thinner, with the sides squeezed flat. This is the visual manifestation of tidal disruption on a macro scale. As you move further into the black hole's vicinity, the rhythm gradient becomes so extreme that even the stable swirling motion of individual particles cannot hold. The alignment of the swirling motion with the surrounding tension breaks down with each passing moment, causing atomic and subatomic structures to fall apart. These structures are eventually dissolved into more primitive energy filaments, completely merging into the black hole's boiling core. So, in energy filament theory, the answer to how much tidal force does it take to tear a star apart is more direct. What's really needed is not just gravity itself, but the rate of change of the tension slope at the scale of a star, the point at which the rhythm of the particles no longer aligns. In comparison, the tidal forces between the Earth and the Moon follow the same basic mechanism, but in a much gentler form. The tension gradient between the Earth and the Moon is just enough to create a slight difference in the loosest locked layer, the oceans, causing the tides to rise and fall daily. However, for the Earth's rocks and human bodies, this small rhythm difference is not enough to pull structures out of their locked phase. That's why we see tides but don't get torn apart. This understanding redefines tidal forces as not a new force added to textbooks, but as the macroscopic manifestations of the tension gradient reaching a point where it starts to unravel the rhythm and phase locking between particles. Tap follow, share it on New Physics, Clear Universe.